Hello folks. What I'd like to do today is show how to create a Telnet Chat Server using ZX and Erlang. So the reason that I'm picking this example, there's a lot of reasons. One, it comes up all the time. People ask this question constantly. Well, Erlang is good for messaging, and it's used in a lot of routing systems and streaming systems, and it's the back end of lots of message services, whether they are long latency systems that like deliver a message to you later, or if they are live chat where all the messages are ephemeral. Erlang's just used in a lot of messaging backends, and people know that there's a merit there, there's a benefit to that, and there's a reason, but they're at a loss for how something like that would be structured in Erlang, because the idea of all these processes doing stuff is kind of confusing, and the little details like ownership of a socket versus listening on a socket, those kind of things are a little bit, strange to come to terms with when you don't have any experience in the environment. So, we'll do a Telnet one here. Part of the reason for doing Telnet instead of doing something like web-based is there's no extra stuff to worry about when you do Telnet. You can actually do really basic Telnet-ish things over Netcat, because you don't need all Telnet is, by default, Telnet is just a line-based text protocol, and it just cuts when it gets a carriage return. It skips the next character because it's usually a new line, but like Windows won't send a new line. Telnet just won't care as long as there's whatever the byte after it is, it can throw away, and it just cuts the line there, and then whatever service you're writing over Telnet can evaluate that line. Now you can put Telnet into special modes. There are it's a full-blown protocol. It's not just text. There are magic control bits that you can send to a Telnet server or a Telnet client to tell it to go into a certain mode, or to notify the other side of a mode, or ask what mode is available on the other side. But by default, it doesn't do that. It's just a line-based thing. And so we're just going to stick with that idea for right now and understand that you can do a lot more stuff with Telnet. Find out the screen size, you can draw stuff, you can get really fancy with it, but we're not going to right now. In this example, we're just going to do a simple Telnet chat server, and one big boost that we get here is that ZX actually templates a Telnet Echo server as the default template for Erlang service applications. If you do ZX create project, the number one thing up there is a traditional Erlang service application, so server-side stuff. Up to now, I've been talking about GUI things in videos, but we'll do server-side this time. And all it does is, if you connect with a Telnet client, if you send a message to it, that message just gets sent to everybody who's connected at the same time, including you. And we'll look at how that works, and then we'll look at where we would add a feature if we want to start editing and adding features, so that this is more of a comprehensible system. And we'll talk a little bit about the program structure in the course of that discussion. So without further ado, let's get into this. So I am in my version control directory that my syncing scripts and backup scripts know to ignore, because Git manages everything that's in here. So create project. So project type, we want a traditional Erlang service application. Project name, Trash Talk, just because. Package realm, we're just going to stick with OTPR because that's all I've got configured on this system. Package name, Trash Talk. Version, that's fine. Prefix TT, that's fine. Author's name, that's me. I could cache this stuff. I think I'll probably add that as a feature to ZX in the future, is probably caching this stuff. So that like once you've answered these questions once, it'll pull them up and remember like, hey, this is what you chose last time. Is it still good to go? And that would just save some typing. The reason I haven't done that yet is that creating projects is like the least common thing that you do, right? When you're messing around, you create a few projects, but when you're really working, you create a project like once and then work on it for a long time. So project description, bringing trash talk to Telnet. Project repo, don't have one. Website, don't have one. That's good enough. So we will have a trash talk directory here. Now I said that the template application is a Telnet server, and just as with the GUI application template that I showed, that I've been showing, this template also already runs. So we can do, we're in the directory right now, right? So we'd use run local instead of run dir. So we'll run the local project. Oh, and I need to do ZXH, not ZX. The reason for ZXH is that I want to have a head because this, that was loud. This application has to know what port to listen to, and you have to tell it to listen to a port. It initializes like blank. Everything stands up and it's waiting for instructions. And you tell it to listen to a port to get it to go. So to be able to do that from in an arbitrary way, I need to have a shell open. So I don't want a headless Erlang server. I want the Erlang shell to open too. That's why I am doing ZXH. Whoop, that was big. Okay. So, all right, built itself. So we see the stuff building that needs to build, and we have this. So let's do trash talk, listen, and then on port 7777. Okay, we're listening. Now let's get, I've got this guy and this guy. So we got lefty and righty. So lefty's going to connect. Telnet. Okay, and what do we see back here? We get a message to standard out that says, I got a connection from, this is localhost translated to IP6. I connected over IPv4, but that's not really important. So somebody's monitoring something. We'll see where these messages come from in a moment. So that's this guy. Now this guy is going to do the same thing. Telnet localhost. Okay. Now I got two clients connected to the Telnet server, and I'm going to say something like say something. And that guy got the message, say something, and then I get an echo back here, message from you, say something. So I can say things too. I can say things too. Okay. Cool. That's all there is to it. Now I could use telnet out, right? Telnet command out, or I can do, I think it's by. Yep. So that's a magic string. And we'll see where that matches on the socket receiver. The socket handler has a clause that can match that particular phrase, and that's a command, actually. That's not just by. That's a command that it recognizes that it should disconnect that client. So we'll see. So here we go. Socket closed retiring was a little different from client saying goodbye, bye, right? So there were two different closure cases, but they were both clean, and that's fine. And we'll see why that's clean. Let's get out of this now. So ZX stop is that's a ZX command that just kind of makes sure everything is shut down in a way that doesn't have any gaps. Obviously, this server doesn't, like, there's no state in this server that's persistent, so we don't care right now. Let me get into the source directory here. Now we've got the top level, like the application module that would be, if you've got two applications and you want to do something with this application, from outside, that is the module that I would probably define the interface functions to, even though those calls would go through to somewhere else. We'll actually see an example of that right here. When I first read an application that I've not seen, and I haven't seen this code for quite a while, the first thing I read is the top level module, which is the application module. Like, how does this thing start? You'll know which one that is because it'll have this. That's the application behavior. This exports listen and ignore, and then start and stop and all that stuff. That's just like kind of standard. That's how things always start up. So you'll always see this, but this exports some custom functions as well. Listen one and ignore. Now we called listen one a second ago, and that was with a port number. Ignore, we can call ignore, and it'll shut the listening socket down, but anybody who's connected at the moment, they're still good to go. They're still connected. So you could have 10 people connect, they're chatting, and you're like, I don't want to see 11, I don't want to talk to 11 people, so let's close the listening port down. The 10 people, their conversation still goes. The system will no longer respond to new connection requests. Now, the reason I'm mentioning that is people ask about hot code loading, and they ask about how would you do graceful upgrades that are not hot code uploads. Hot code loading is a really slick thing to use in development. I do it quite a bit in development because it's just easy. You made a minor change, and you just, you've already got some state in the system. It's already built up and doing something. And you make a change to a module, and you check if it does what you wanted it to. That's great. But in production, hot code loading is fantastically useful. It's a critical feature in certain environments. Like you have temperature listening stations way out somewhere that you can't get a service guy to, or it'd be prohibitively costly to send people out. But you need to update it, and it can't shut down no matter what. That was the situation that Ericsson was in. They weren't doing temperature monitoring. That's from a different example. But Ericsson, they're running phone switches everywhere. People have live calls going on. They need to do an update, but those calls never end. So how do you update a system that you can't shut off? There's two approaches. One is you have two systems, and you deny new connections and push them all over here. So retire from availability, from the worker pool availability. And then as any work that's ongoing over here gracefully concludes on its own, as people hang up the phone or people stop chatting, or in the case of this Telnet server, as chatters get off of the system and log off, new connections would all be diverted to a new node over here. Once this is clear, there's no clients connected anymore, then you could shut down, do a destructive update, do whatever you want, because that's no longer in the worker pool, right? Once that happens, then you do the same thing over here. This guy retires from the service pool. All new connections are directed to the already updated server. When this guy has no clients connected anymore, then he can do a destructive update. Or you just schedule downtime with your users and say, hey, there's going to be an outage for like, a minute or whatever, and restart stuff. In the web world and in modern service world where we have, we're not deploying to phone switches out in the middle of nowhere, or to so many devices that we can't get to them. We're deploying these days. I mean, we're running on like full-blown servers that have complete Linux installations on them. We can access any kind of software we want. We can stand up, 50 VMs and have them pass load around each other. It's like, this is not a problem that we have. We're not facing the hot code upload required situation that Ericsson had. So I mentioned all that to say that hot code uploading is really cool, and it is a really interesting feature, and in some situations it is absolutely necessary, but it is difficult to test every possible case of state updates. If your state record, or if the shape of state in this version of a process looks different from this version of a process, and you don't convert them properly in every possible situation that might exist, there'll be a fault and it'll crash. Now, we can handle crashes. It won't crash the whole system unless too many of them happen at once. And that's something we can decide if, what's the maximum number of crashes that we're going to accept within a given number of seconds. We can define that. We can accept a ton of crashes at once. So it's not that I said unless too many happen at once. I mean, unless our limit was triggered that we defined ourselves. It's not like a system. It's not like Erlang panics if too many crashes happen at once. But we don't want a service interruption so bad that we're willing to do this extreme amount of work to create a hot code upload, a hot code loading, a self-updating system, go through with it, test it, and then push it out, kind of biting your nails that nothing goes wrong out into the world. That's a significant amount of work, and you wouldn't want to do that just for like a web service or something that you could just pass load and then, pass load over, do a restart, and pass load back. It's much simpler to just, load pass instead of doing a code update, a hot code reload. I say it's simpler. It's simpler in human terms. How much developer time effort you're gonna put into that. So I'm mentioning that because this ignore and listen. This is your path. Like you would do some equivalent to this. Like ignore one, if we had a bunch of Telnet services, we were running IRC, a large IRC network or something, and there's lots of different nodes around the world, and they're all reflecting messages amongst one another. And you want to take a node down, you would just stop accepting new connections, let everybody retire from that, and then take that node down. And all those clients would just connect to somewhere else in the meantime. And this is kind of the way you would enter that mode, is you would start ignoring new connections. So anyway. If we call listen with a port number, it's going to call client man listen. Now, we could have this is obviously an exported function from client man. Why did we define this on Trash Talk? Because this is something that you're accessing from outside of the application. I did it from the shell just now. I don't want to know the internal details of like where listen's actually defined and find that module and call it. I just want Trash Talk as a system. I just want Trash Talk like as this system from a top level view. I want to say, hey, Trash Talk, listen here. Or hey, Trash Talk, ignore new requests, new connections. Instead of thinking, wait, inside of this system, what module is able to listen and go digging through garbage? And that's a mess. So this is a simple way to do it, and it's much nicer for your users if you define top-level interface functions where Trash Talk is this abstraction. It's this server. It's a service, and you just want to talk to the service. Define those interface functions on that service, because the other way sucks. Making people have to dig through your code is like it's dumb, and it's also bad for you because like now I remember where this is, and I haven't seen this in a while. So we know how that starts, and we know what application does, right? It's going to start a supervisor. So let's see what we got. Why did I list twice? Whatever. Let's get into, this is the top level supervisor. You will notice that all of these templated modules have kind of extensive commentary, and they have links to documentation references. The reason for that is to explain what's going on and help especially new Erlangers. An experienced Erlanger, you're going to change these comments anyway because the system's not going to fit exactly what you want to do. This could be we might use this as a template and then from here change everything out, and it's actually like a data center battery, service battery, backup battery monitoring service or something. It might be anything, but the basic template for the application is going to remain the same. So all this stuff would change if you're writing a big system for real. We see we've only got one client here. We've only got one child here, and it's called TT clients. In the same way that Trash Talk is an abstraction that we're providing interface functions to for any other application or humans that want to interact with it from a top level, within the system, we structure every major component of a system as its own little service tree. The reason for that is partly for robust behavior and partly just for to reduce cognitive complexity, to kind of regularly do things, structure things within a certain idiom or according to a certain idiom so that it's like instantly recognizable to anyone who is not familiar with the system. They've got something to lock onto cognitively instead of having to read everything in the system, because you wind up with that situation where if everything's custom all the time, you have that situation where to understand anything, you have to first understand everything, and that's just not where we want to go. So as its own little component, we can understand that there is a top-level service within this application, and it's called clients. The name of it gives us some indication what it does. It handles clients. How it handles clients, we don't know yet, but that's what we have. That's the top-level service. So let's open that one, TT clients. So Trash Talk Client Service Supervisor. Yet another supervisor, right? We're going to see what children this has. And you notice the previous code looks really similar to this code, right? It's like the only difference is that we have an additional child. Again, idioms do things the same way lots of times, and your eyes lock on, what am I looking for in this? Well, this is a supervisor. How do I know that? It ends in _sup. Even just the names like that. Using regular naming patterns makes it very easy to interpret what a project does. So, clients is the top level supervisor. It has, below it, it has a client manager, client man, and it has a client supervisor. Now this supervisor is a simple one-for-one, meaning that it can make an unlimited number of copies of a single process definition. So in this case, when one client connects, we want a listener waiting, and then as soon as he's got a connection, we want a new copy of that to start up as a new process waiting for the next guy to connect, right? So a simple one-for-one supervisor is what Erlang uses. It's a supervisor type that can let that happen. And I recommend that you go, if you don't know about this stuff at all, if this is all new to you, I recommend going to read the supervisor documentation. There's a link to supervisor documentation inside of the template here too. So if you just run ZX, get a template like this and go follow the links, you can find everything. Client man. Now, client man man is short for manager. The client manager represents anything that has like _man after it. That means that indicates a manager for a service. So I said that we've got the application. We had the main application supervisor that was just, TT _sup. Then it only had one child that was this guy, right? The client's supervisor. And that's the clients itself is just the abstract, that's just the chunk of the system that represents clients, overall. But we can't talk to that supervisor very easily. Interrogating a supervisor is a little bit weird. And putting a lot of like extra code inside of a supervisor module is not recommended. They should be very boring. This should be almost rote code. And the reason is this represents the supervision tree structure that you have within your program. They shouldn't be fancy. Don't write dynamic supervisors. You don't win the way that you think you would win when you try to do dynamic supervision. It's better to just define services like I'm talking about in chunks. There's a couple of abstract cases where that's not true, but if you're going to follow OTP stuff and you want a robust program and you're not trying to run off and be a, Wild West code slinger, doing things a regular way is boring as good when it comes to supervision. All the exciting stuff is going to happen in the clients and sometimes in the managers. So this guy manages clients, as his name indicates. He knows which clients are on. If the clients authenticate, if they have usernames or whatever, this is the guy that would verify that that's true, or get them in touch with whatever would be able to verify them. If you need to look up a user by name or something like that, or look up a current connection, because that's the thing. These users are actually just connections, right? If you need to figure out which socket represents a given username at the moment, then that's the guy that would know the answer to that. You're not going to be able to get that stuff from the supervisor because the supervisor has no concept of like sockets or usernames or authentication or any of that stuff. But you got to have somewhere to put that. And you don't want to just have one God process at the top that has all the state for every subservice, because if that goes down, everything goes down. You might have a central configuration thing, so you can do dynamic configurations and restart services with new states and stuff. That's actually a good idea, and we use that a lot. But inside of a given service, this is a client service, but if this was a game, we would also have a game world, right? We'd want to define that. What lives in a game world? Mobs and world objects live there. So you would have mobs and world objects if world objects are processes, if they're dynamic things. They usually aren't, but they might be. But you would have the world, you'd have mobs, you might have a game system that's specific to itself. You may have a chat thing that's like chat channels. If you have chat channels and chat commands and all that, those aren't clients, right? Here, clients are sending messages through the manager, and he's just sending them to everybody. It's an echo service right now. But if we want to make this into a chat server that's got channels, maybe it's got logging history. Maybe that logging history has an interface to the web also. If we want to put a web interface on top of this, that's not in these clients, right? That would be web clients, and we would make a different system, a different structure over there to handle web requests. They'd be pulling from the same data pool, but that's two different interfaces, two different ports. In most cases, there's ways we can make a single port handle some stuff, but that's an advanced topic. But generally, we would have two different ports, right? An HTTP port and then a Telnet port, and they're not the same. Two distinct sets of clients, and maybe they can communicate to each other, but they're not the same thing. So that maybe we have a GUI client, same way. Different protocol, maybe it does everything in a completely different way than Telnet does. Because you may have some metadata about the current state of the connection that you need to communicate. So anyway, all these things are chunks of a system. You don't want to have one thing that knows all the live state at once, because if it goes down, the whole system's down. So you want to protect whatever's at the top, and the best way to protect whatever's at the top is don't put too much at the top. Keep these things separate, discrete services. Now, some might say, and some people do say, that Erlang systems are inherently swarms of microservices. That's actually true, but I don't like buzzwords. So Erlang is fully buzzword compliant, but that is an accident of the nature of the system and of the nature of current buzzwords right now. Anyway, so we'll look at the client supervisor is not very interesting, but we'll just see how it looks. It's going to look a lot like this, right? But its task is going to be very different. So start acceptor. Okay, we've got a start acceptor. That's exported. What's that do? This spawns a first listener at the request of the CT. Okay, so start acceptor is how we get a listener to begin with. Who calls it? We're not going to care about that right now. When listen's called, the next listener is the request current listening client when the connection is made. Okay, so it looks like we're probably calling TT client start, and then that actually is calling this. So we'll see. It doesn't really matter. So start laying in it. Yeah, so we've got a simple one for one supervisor, which means it can start an arbitrary number of peers that are clients. Like the things, this is where the clients live. This is the process that owns the clients. Now, we can accept up to one crash of a client every 60 seconds. That's what this means right there. So let's hop over to the side and check this guy's peer, which is the client manager. So this is where listen and ignore are actually defined because he owns the socket. Enroll and echo 1. So let's see what these mean. We've got, this is the state that, this is the sum total of state that this process is going to keep in memory. This is his view of the world, is port number, can be none or a port number. Listener can be none or a TCP socket. Clients starts out as an empty list, but it's a list that is supposed to be of PIDs, so it knows who's alive. So we've already got some kind of idea how this works, right? We know what listen and ignore do. We already know that. And we know that that should affect these two. Then we've got enroll. A client would enroll to let the manager know, hey, I've got somebody. I've got a customer. As opposed to waiting. If you're waiting on the socket, right, you're not enrolled because you're not talking to anybody. After you get a connection, then you would enroll to notify this guy that you've got a client. And echo, pretty clearly, that just means whenever a client socket handler receives a message, it's going to tell the manager, hey, echo this to everybody. And that's easy because this guy knows everybody. So if you send him the message, he can just forward it to every process in the client list, and that task is done. And that's how those chat messages get sent around. So listen, port number. Okay, remember, this gets called in the context. These are exported functions, right? Service interface. Interface functions that are exported are called in the context of the whatever process is calling them. So the top level module called this. In that case, when we typed it into the terminal earlier, the Erlang interpreter's PID, that was the one that process is the one that actually called this. Because it called through to this, right? So this was executed in the context of that process. At this moment right here, gen server call. If you look in the gen server code in the OTP source, you will see that gen server call actually initiates a message being sent to the target process. Now the target process here is defined as module. That's a macro that means this thing's name. When this thing starts up, it's given an atom as a name. So we don't have to know the process ID of this particular process to send it a message. So this is sort of a shortcut. The shorthand that we use is if it's a named process, then we don't use the PID. We can just use the name, whatever the name is, which has to be an atom. And that will be the name of the module. So we're just putting module here. So we're sending to the manager, which is named TT client man, a message, listen, port number. Now, there's a return value for this, right? So listen, this is the type spec. Listen takes a port number, which is defined here as a port number, which has to be within legal range, right? Result is going to be okay or error. Now, because it can return a result that's not just okay, this is a synchronous call. The calling process has to wait for a response before it can continue execution. And that's what this is, gen server call. Now, the next interface function here is ignore. And it just returns okay, and it doesn't wait. This is a cast. So the form of the message is the same. The addressee and the message. Gen server cast is going to send the addressee, which again is the same. It's this process. It's the client manager. It's going to send just an atom. That's the whole message. Ignore. Now, when this function's called, you don't wait for a response. You get immediately OK comes back, and you're continuing processing. It's a non-blocking call. It's a non-blocking message. So this is asynchronous communication. This is synchronous communication in the gen server paradigm. And I recommend that you use the gen server paradigm as much as it fits. There's some cases I don't like to write gen servers or gen whatever. We'll see an example of that in just a moment, because I usually write socket handlers as pure Erlang processes and not using the OTP. Well, they'd use the OTP stuff, but they use it through a thing called proc library. So they appear as gen servers to the rest of OTP. They comply with all the stuff that's expected of an OTP compliant process using that library, but you don't have to do all the gen server stuff. So enroll, this is the client. This section of the code is the client process interface, meaning those workers over there that are accepting socket connections. They can call enroll Client register here when they establish a connection. Okay, so as we had assumed looking at the top, that's what happens. Remember, the caller, which is the client, that's the context in which this function body is executed, right? So we see enroll and there's no arguments. We're like, well, who's enrolling? Self, right there. Self is enrolling, and the reason we can call the built-in function self that returns the PID of the current process is because, as I said, enroll is being called in the context of that client that's calling. So it's sending another asynchronous message to this manager process, and the message is enroll me. And that's it. Now we don't wait for a response. We're assuming that the manager is going to figure out on its own time how to do things, how to enroll this guy, and the client is got better things to do than wait around for a confirmation or whatever. Because we know the message isn't going to be lost unless the manager dies. If the manager crashes, then we're going to know that it doesn't exist and try again. So echo message, very similar to the above. Tells the manager broadcast message to all clients. Echo receives one argument message. Again, we're in the context of the client itself that's sending a message, so it sends to self. It sends its PID along. So it says, client manager, echo this message from me. Startup functions, you're going to see this everywhere. This is like basically boilerplate code. Init, none. We're not taking a start argument that means anything. This could just be a blank underscore. This could be anything arbitrary, and we could just not assign it. It doesn't matter. I just use none to match directly. Init is the first place in the code that is called in the context of the current of this process. So like from this part of the code down, from this line down, we are talking about execution in the context of the manager himself. And that's the PID, that's the manager's PID that we're operating under right now. So, and this is the first moment that that life begins is init. So, okay, IO format starting. That's going to send a message to standard out starting to let you know something's happening at all. Notice that we don't put any data in the state record. It's just got the defaults. Port numbers, none. What else was there? Socket, the listener was none. And the client list is just an empty list. Why would we not start this with a port number to go ahead and listen to on startup? The reason is that this is process initialization. The rest of the system, which might be arbitrarily large, still has yet to be initialized. We don't, if we turn this into a really large game server, for example, there might be a lot of stuff to load and start up. We don't know how long that would take. We don't care how long that would take because we're going to start up not listening. What we can do instead is that, remember that application module, the top level module, trashtalk.erl, that module has defined on it a listen function, right? It also has those start functions. The start functions, you could say start application, this application, and then right below that is the last step. You could add listen to some port number that you get out of a configuration file. That's the place to do it. Don't put it in the initialization code for a number of reasons. One, a socket is an external resource. You don't want to make startup depend on an external resource. After you initialize, the last thing you do might involve external resources, but you don't want to touch anything yet. We know that we can read the memory of this. We can read core. That's good enough for initialization. And that's all we want to get into here. The setup steps that are aside from process instantiation, we do that stuff later. So we're starting up blank, not listening to anything. It's just dead blank sitting there. It's just waiting for an instruction. And as I said, we've got another place higher up in the chain where we can put a final instruction to listen, which we can do in a moment. So, Gen server message handling callbacks. This is the generic Gen server code that you always see: handle call, handle cast, handle info. Gen server call is what this is here. These have to return a response to the caller, because if they don't, it'll crash the caller, because the caller's blocking waiting on a response. Handle cast, you don't return anything because you got nothing to return anything to. You have nowhere to return a message to. You can set up asynchronous communication where an address is passed in, you can send a message back later while he's doing other stuff, but the caller is not blocked when a cast comes in, right? So the Gen server handle call is handled here. That call listen port number, that's this message. We're matching on that here. If this clause matches, then we're going to do listen, and that'll update the state and provide us with a response that we will reply with the response in the new state. Well, the state's not the response, right? The response is this. New state, we're actually passing this back up to the callback, the Gen server handling code, which is an OTP. But it's in the context of this process. And the casts, like I said, those are asynchronous communications, and then handle info is also asynchronous, but those are like naked messages. If you just use the Erlang primitive, the asterisk, send a message somewhere. That primitive operation to send a naked messages are handled by handle info. And some system stuff comes in there. And we'll see one example in this, because we have to have a way to catch that a client that we're monitoring died or retired, which we saw 2 examples of, right? I did buy and it left, and then there's also the case where the socket just closes, or maybe something in the client handling code crashes. Then all those cases would send a suicide note to this guy, and that'll be a naked message within the system. Something to point out here with code structure and style, I've been talking a couple times already in this video about doing things in a regular way so it's easy to lock onto what's going on and figure out what's happening if you are coming to a system for the first time and you've never seen code before, which you guys haven't seen this code before. So it's all structured in the same way kind of everything else is. And you've got your interface functions at the top of the module, and those are exposed to the outside world, and 99% of the time those calls are going to be in the context of other processes trying to talk to this one. Below that, we have our initialization startup stuff, start link and it, right? Then we're in this is the main loop right here. Like when you're thinking, where's the main loop of this thing? The main loop actually lives back up in the Gen server module, and that's in the OTP code. These are callbacks that know this module is the active one right now, so I'm going to call that module's version, that module's definition of handle call, handle cast, handle info. Depending on what kind of message I just received, I'm going to call down to that, and we enter this module here. So when you're thinking about like, how does a Gen server do anything? A Gen server does something because it receives messages, and those messages are all handled in these 3 functions, these three callbacks: handle call, handle cast, and handle info. There's some system stuff that is other callbacks, but like, you almost never really care about those much. That's system stuff that's for the system until you get into really special cases. So handle call is receiving a message called listen. Now, remember I said regularity. There's a theme will emerge with all this code. The interface function listen sends a message that is tagged listen. Inside of here, we could define the do listen function, could be defined right in line here. And, instead of having handle call listen response reply, and then that's the whole clause, we would have handle call listen, and then blah, like all this stuff. And then the next handle call clause would be like way down there somewhere. And these could be arbitrarily large. They could be arbitrarily dangerous segments of code. We don't know. It is much easier to comprehend what a project does and get the whole thing in your head at once if you, when you first open a Gen server, you jump down to you first read the interface functions, what their names are and what the comments say that they do, and then look down below that to handle call, handle cast, and handle info, and it will show you, it spells out at a glance what messages are legal to receive. And then below that, you typically have an unexpected handler. The reason for that is we don't want to have a case where an external message coming into this gen server is going to crash that server. That would be dumb. So a rogue message coming from like somewhere, coming to this process ID, and we don't have a handler for it, we don't have a catch-all, would be bad because we could totally crash this manager just with any malformed message. And so I've always got a catch-all, and the catch-all almost always logs or prints the standard out something, lets us know, hey, I got a weird message. I don't have a handler for this. And when you're developing, that's important because you might forget that you changed the form of something or just some stupid little typo somewhere, and you get a crazy atom. You don't get listen, you get like listen with no T or something silly like that, or you misspell something. So you want to have a catch-all handler to let you know what's going on instead of blowing everything up all the time. So anyway, listen interface function sends a message that's tagged listen, and that's going to result in a call to a doer function. The inner function where listen is actually defined is do listen. Now, listen. Is that redundant and annoying? It's boilerplate? Yeah, kinda. But it's very regular and it's super easy to understand. And easy to understand is kind of what we're trying to go for here. That's the most important thing about a system for humans reading it, if you're going to maintain code, is to have some concept of what's going on. Sometimes I don't put these type specs in here. The template has them, just to crunch everything down. So, you see the whole, like, what's this guy do? It's all right there. And then when we do listen, after you type this stuff and you know what your module is kind of supposed to do, you know what your process is like supposed to do, you could write these and then like stub them out. Just write a do listen that has like blank blank and then returns a dummy response in the same state, and then worry about implementing it later. When I'm writing new features, I often do that. I'll put an interface function at the top that's going to send a message of whatever appropriate form, put a handler for it in here, and then write a stub at the bottom that would be this function's definition, but it's not really defined yet. And I'll just return some dumb, something silly like not implemented yet, like an atom. I think NYI. I've got NYI stuff all over the place. It's like not yet implemented is a little atom that means this hasn't been implemented yet, but getting this message, like the pathway to getting it done, is almost finished. So the last step is just actually writing the function, which may be easy or hard, depending on the task. But templating the code is not hard. And understanding what the code does is not hard. And finding gaps in the code is not hard. Because you don't have a maze of stuff happening all inside of these gigantic handle call clauses. You can also see which functions are called just for side effects, which are called for state updates, and which are called because they should be returning a response. Do listen clearly returns a response. It's right there. And that can only happen in handle call. In handle cast, enroll, do enroll. This was a cast, so the response is already sent back okay. But we have to update the state here. So do enroll, right? Enroll this PID, do enroll PID into the state. Is going to return a new state. So we have some idea already kind of what has to happen here. And we saw the way the state record's defined are like we can already envision in our mind what has to go on inside of do enroll if we know this much about the program. Handle cast echo message sender. Do echo. Now, there's no state update here. We're not remembering this message. We're only forwarding it. So we're getting the atom okay back, and we're matching on it. That's important to do. In Erlang, the equal sign is assignment, like in other languages, but it's also assertion and matching. So I've got an atom here. An atom can only match itself. That means that this use of the equal sign is an assertion that do echo was successful. And if it wasn't, we should crash right here because something's bad wrong. If we can't just forward messages to a list of PIDs, something is bad wrong in the code because that's such a simple operation to do. So we're matching on OK to make sure that actually happened. some people will omit this. They'll just, take that part out. And I recommend not doing that. I recommend always, like almost every line of your Erlang should be assigning something or asserting something or matching something. Because you don't want to throw these results away in most cases. There's a couple of cases, just a handful, where you don't want to do that, but here you definitely do. Ignore. We're going to update state. That was an independent procedure. So again, no response to the requester. And then we've got the handle unexpected case. Handle info. So the manager has to use Erlang monitors to monitor the child processes. What a monitor does is when you assign a monitor, you've got a reference tag to that monitor. And if that monitored process, whatever you're monitoring, goes down, crashes, dies, whatever, for any reason, you get a down message with the monitor reference that value that you got when you created the monitor. This is telling you that it's a process. It's not a socket or some other thing. It's a process that you're monitoring. The PID of the dead process and the reason that it went down. If it went down with normal or shut down or whatever, it would just say, normal or shut down. It would have a reason. If it crashed, though, it would have like error and then blah, all this stuff. And that will show up. You can log that information and find out why something went wrong and kind of track down what went wrong. So it's important to capture all this data about the dead process so that you can debug. And there's other system tools that can help with that also. But this is how it's done right here. So handle info, if we get it down, we've got a separate function called handle down and new state. Now we can imagine exactly what this does. In the state, we have a list of clients, their PIDs, right? If a client goes down, we need to remove that PID from the state. And then that would return new state, and we would move on for the next iteration of whatever's going to happen in this program. Code change, terminate. Those are just standard callbacks. You can read this stuff about what needs to happen in these, and then I think these pages link to stuff I think called Otp Design Principles, and it kind of explains how why those things exist. So we had do listen. This is where do listen is defined. Do listen receives a port number and the state, and it returns a result and the new state. And as we saw above, the result needs to be okay or error with a reason. And reason is interesting here. It would be listening at a port number to tell the caller, hey, I can't listen right now. I'm already listening on this port, which could be the same one you passed, but it can't listen twice. So do listen, port number, state, port number none. Now we could make this independent also, right? We could add a new clause up here that has port number and then matches the same port number. And if that's true, just return OK, because we're already listening. In this case, we've just decided to say if the port number is assigned as none, then we're going to open a port and listen. Here we have socket options. Socket options. Now note, this label only occurs one more time here. This is written that way to let you know what this is, because if you're not familiar with GenTCP already, this stuff might not make any sense unless you've already done a lot of network programming elsewhere, because a lot of these atoms are pretty much the same. They're the same form that you would get when you write C socket code. But not everybody knows that stuff, so these are socket options. That's an easy label for it. It's documented in place. Don't need a comment. And then they're referenced here. Now, this list could be defined in line here. That would be a very big, ugly, weird line, and it would be annoying to read. More annoying than going socket options. Okay, socket options are going in here. And then caring about the details later. Because I don't care what this says right now. Not really. Listen to port number with those socket options, we get a listener. Now that's a socket. This was a port number, right? That's an integer. This is a socket. Totally different thing. Then we're going to start a client with that listener. Now, this process, the manager is the one that created this listener. So it owns that. But it's not listening to it. It's not blocking on receive, right? It's not blocking on accept. It's not waiting to accept a connection. The client is blocking to accept a connection. So it's blocking on TCP accept. This thing owns the socket. The client is actually listening on the socket. Because that client is blocking, it cannot respond to messages right now, which means that you can't get data out of it unless it's like iteratively like polling. Okay, wait for this many seconds on here, and then I'm going to check this, and then am I connected yet or whatever? That's a crappy way to do things. So we're separating the tasks here. We're saying you own the socket, you own the service, you're in charge of it all. This guy's a worker. He's got no state, nothing. He's totally free to just sit there and block on accept. We wouldn't want to do that here and then pass an accept socket over. That also means this guy can shut that socket down, right? He can receive an ignore message. The client can't do that because he's blocked. So we return the atom OK. We assign the port number and listener. So in the next turn of the wheel, those are going to be assigned. They won't be none anymore. And if we receive this, call, we don't care what the port number is in this clause, right? This version of do listen, because the port number is not none. It's a port number, which means we're already listening. So we're going to return an error, already listening on this port, which is this error message here. And we're going to format to standard out the same thing. This is going to be the PID of the manager process, just so that we know who's talking to standard out. Do ignore, it works very similarly. If we're already not listening, we return the state. If we are listening, we close the listener and then assign none and none, so that this would work properly again later. If we did ignore and then we do listen again, that'll work properly. So we got to reset the state down here. Do enroll. As we saw in the comment above, this is what the clients call. So the client PID in the state. In Erlang, case is used instead of if for almost everything. If is used for like ranges that you want to cover a full numeric range with like multiple different checks, not just a simple true false, but if you have several, like if it's from 1 to 10 and then 11 to 20 and so on, up to like 100 or some fixed range, then you would have an if, and you've got several different possibilities in there. If you have pretty much any other conditional check where you're going to be branching, we do either you do the thing in a function head match, or you match inside of a case. A case is essentially an opportunity to create an arbitrary match, an arbitrary matching situation inside of a function body. All Erlang scope is defined as the body of the current function, period. And I say period, and then that's not quite true inside of a list comprehension, or sometimes a lambda. But the general rule, with those two exceptions, is that scope is defined as the body of a function. And there are no sub-functions except for lambdas, and those close over state, which if you watch the dispatching closures video that I did yesterday, you'll see exactly how that works, that a lambda can close over, outer body state. And that's how you would create a closure in Erlang. That's pretty much the only reason that we use closures or lambdas in Erlang, actually, is most of the time we're closing over some state that's been built up in the current function, and we need to keep that as a constant reference instead of iteratively calling something all the time with a single argument over and over. Or world passing. It avoids world passing in some cases. Anyway, case is our do it all. That's the Swiss Army knife conditional branching thing. And again, the reason is that it lets us have a state that exists within a function body and use an arbitrary situation to match on something the same way we would in a function head. I could write do enroll this is do enroll 2, right? I could write a do enroll 3 that just has as its first argument list member PID clients, the result of that, true or false, as the first argument. Match on it, and that would eliminate this case completely. I don't like doing it that way with a single level. With a single level, case is nice. If you get to multiple levels of case, if you're nesting cases, I usually do break it out to another function. I have like a do enroll 2 or something, because that jigsaw, it's not jigsaw. The sawtooth code thing is something that's like a pet peeve of mine, and you don't have as many entry points for testing. And especially if you're building up a lot of state inside of the body of that function, you really want to break that down so that you can individually test one clause, one segment of an extended procedure, especially if there's a lot of outside state that it's building up, like from external resources, across a socket or something. So anyway, if the PID is a member of clients, then that would be true down here. We don't need to do anything because it's already in clients. That client accidentally called enroll twice, so we're not going to take any action. If it is not a member of clients, if this returns false, we're going to monitor the process. So we get that monitor reference. We're going to announce to standard out that we're monitoring this. And then we're going to add that PID to the list of clients. So if it's already a member, don't do anything. If it's not a member, do something. That's how this works. And this doesn't say true, false. It says false, true. The reason for that is the case that we're looking for, the case that we expect. Typically, people put that on top. It's arbitrary in Erlang because these aren't really Booleans. These are atoms that represent Booleans, but atoms are a general type. I mean, this is an atom also. We could put any kind of match in here. Any data shape, anything could match in here. And that's very common in a lot of other code to do like very complex case matches because you can massively simplify checks instead of having a maze of conditionals that have to check a whole bunch of things, a whole lot, if you have stacked up logical cases, then with lots of possibilities, case is kind of a way to compress all that down into a very simple statement that you can just look at the matching list and go, oh, that's what this can do. Or those are the possibilities for branching right here in a flat way instead of trying to condense everything down into like a single numeric response or result that would be used in like a select statement, or doing a whole bunch of sawtooth code with if then or if else, and doing lots of all these just this maze of conditions. In other languages is a little bit simpler to do with a case. So that's why we use case for kind of all of our, I should say we use matching for all of our conditional branching needs, with the exception of numeric range checks. And matching can occur in a function head or inside of a case. So anyway, do echo. We get a message, which is going to be a string, a sender, and the state. So we're going to take this message. Well, I mentioned closures. This is a closure right here. This is a lambda. This is a function that has no name, except that I actually give it a name, because I don't like defining stuff like this in line, because sometimes lambdas are quite large. Anonymous functions can be quite huge if there's a lot of stuff going on, especially when you're dealing with input from the outside world. So I like to give things a label to make the final thing read more smoothly. So for each send to the clients, so for each client, send something. Now, send is a label that represents this lambda, and this lambda closes over the sender and the message right here, right? So it receives the client, and it's going to send a naked message. This is not calling an interface function, right? This is a naked message relay sender message. And we'll see where that exists on the client. And then the handle down function that we saw before, if we get that down message from the monitor, we'll get the monitor reference, the PID, the reason, and the list of clients. So this case, we expect that any down message we get, because all through here, the only monitors that we're establishing are clients. So if we get a down message, it better be in the client list, right? I mean, it really should be. So if this PID, if the down PID is in the list of clients, we're going to delete the PID from the list of clients and return the state. But if it is not a member of the client list, we're going to reconstruct the unexpected message as it originally was received right here. And we're going to notify the system. In this case, we're sending it to standard out, but if you evolve this project even just a little bit more, you would want to start logging that message and say, hey, I got something crazy. So this is kind of an extension of the unknown unexpected clause of the handle info, right? So this thing here is an extension of, where were we at? Handle info, this thing right here, is kind of redefined down there. So now let's look at the client. That's the last thing in this. We've discussed the whole project actually, which is TT client. Trash talk client. An extremely naive client handler, which that is true. This is very, very naive. It's got one thing in state. It doesn't know anything except for its socket, which starts out as none. And let's see how we start. Remember we had start and then listen socket that came in. It's going to return OKPID or an error. Now we were matching on OKPID. If it returned to error, that would match and that would crash the manager and that would actually kind of blow the whole system up, which is what we would want because this thing had better be able to start up. Start listen socket, client supervisor. Okay, remember we saw start acceptor in TT client sub before. That's how this works. So this is like a polite little interface to say, start me with the socket. But in the background, what's actually happening is here, this is calling up to TT client sub. We could eliminate this and we could just have TT client sub start acceptor called directly from the manager. There's nothing wrong with that. This is just, what would we call it? It's kind of a stylistic decision to have the interface here. It could be defined back on the supervisor. You could even call the supervisor start child TT clients up. You could do its own internal call from outside also. It's again, these are stylistic decisions. I think this reads pretty well, and I'm very big on readability, which you've probably already noticed. Oh, okay. I need to go back to the top of this guy. Notice there is no behavior defined here. The reason is this is a pure Erlang process. This is not actually a gen server, and we'll see the difference in just a moment. Listen socket. We're using proclib's version of start link. We're not doing gen server start link. We're using proclib start link. Gen server is defined using gen server, gen FSM, gen statem, all the gen stuff. All the OTP standard behaviors are defined using proclib. And that is because proclib, that module abstracts away a lot of OTP kind of deeper functionality like stateful inspection and runtime inspection. A lot of the really magical runtime inspection stuff that Erlang lets you do and management tools that you have available to you because you're using Erlang exist because of proclib. And the way that all that OTP, gen server, gen state stuff works. So we're going to comply with that here because we want to be able to use Observer and look inside of this process at runtime. And that means we have to, just like we have callbacks that we have to define for gen servers, if we're going to do things with a pure Erlang process and write our own process our own way, we have to comply with the style of system messages that proclib or OTP may send to us. So there's system messages we need to be waiting for in any receive clause that we write. Maybe not any receive clause, but most receive clauses we want to have the option to respond to these. That means that typically you'll wind up distilling you'll have a main loop. Usually it's just called loop. And it's set a certain way. And depending on what messages you receive, plus the system ones at the bottom, and your reactions to those, you'll be able to comply with OTP, but still write your own code your own way, which means that you also avoid the lookup time of that callback, the callback module lookup from Gen Server. So anyway, start link, listen socket, proclib start link. So this is actually going to create a process here. Module, this module, init is the function we're going to call, and these are the arguments. You will see in Erlang documentation and examples all over the place, you'll see spawn, module, function name, arguments. Module is always an atom, which this translates to an atom. Function name, another atom, and then a list. And it might be an empty list, but this is how you define the arity of a function. So if it's an empty list, that's init 0. This is going to actually be calling init 2. Now we have that flexibility here. We can init is always init 1 normally. We can actually make an arbitrary sized argument list here because we're back up a little bit deeper in the system. So anyway, module, function, args, MFA. You'll see MFA all the time in Erlang documentation. So that's what's happening here. We're calling this module init to start. So this is actually going to get we're spawning right here. So this, from this line downward, we're actually operating in the context of a client process. So this is going to receive a parent. That's why self is here. Remember, the supervisor is calling this. So supervisor is the parent. So it's calling with self, the supervisor's PID, and then it's getting to listen socket, and we're not returning anything. Because remember, this process is going to keep on going through its loop. So there's no return value here. That's explained up here, probably. So listening, he's just announcing I'm listening. Debug options, we're not setting anything, but we do need the result of this function because, again, I said we're conforming with a certain style, and the style of the OTP loop type functions is the main, OTP main loops have 3 arguments: parent, debug, and then the state. And the state can be anything. In this case, we've only got one thing to keep track of, and that's the listen socket. So it's still, we're not putting the listen socket inside of like the state record. We could, but there's no point right now. Listen, parent, debug, just as we said, parent, debug, and then the state. This is the only bit of state that we got. When I said that we're blocking, the client blocks on accept. This is what I mean. We're calling gentcp accept, and this function will not return, so this case statement cannot compare to anything until it gets a return value. It's going to block until somebody, like a Telnet client, connects to the, until a TCP connection is made to that particular listing socket. When a connection is made, we'll get OK socket back. If the owner of the socket, which was the client manager, closes the socket, this will return a value instantly, which is error closed. So we have these two cases that we're matching, possibly. So if we listen, if we call trash talk listen, this will happen, and this will be the first guy waiting for this is the first client listener just waiting for someone to connect. If we then call ignore, the manager that owns the socket is going to close the socket. That's going to initiate a return value from gentcp accept that will be error closed. And then this guy's going to actually exit. He's done. He doesn't, I don't want to live anymore. He's gone because he's got no job to do. So he's off. If a connection is received, he's going to call his own start. Remember, we had TT client start was called by the manager that for the first one. Well, this guy is actually going to call his own successor by himself. So immediately, as soon as the connection is received, a new one of these is spawned with that same listen socket. Because we just got our talking socket right here. We don't need that. We don't need the listener anymore. So we're passing it on to the next guy. This is the moment where the torch is passed and the next client listener is instantiated. And it's spawned and it's waiting exactly like this guy was right there. And that happens like super fast. So, that's just how this will work. The socket that we got, that's what we want. This is the new connection now with that Telnet client out there on the network somewhere and us. And as long as this is open, we can talk to that guy, ostensibly. INET pure name, that's how you can take a socket and ask like what's the address. You can like inspect the socket a little bit using some of the INET functions, and that's all that's happening right here. There's ways to pretty format that. As you saw over here, this is what's actually coming out as an IP6 in internal format, right, which is a tuple of values. And the tuple form's not very pretty. And if you don't know anything about network addresses, then that just looks like crazy anyway. So you would want it formatted in that normal, like if it's an IPv4 address, you would have, like the local address 127.0.0.1 or whatever. There's a way to format it like that also if you look in the INET. I think it's called INDA, numeric to something address. I don't know. There's a way to, there's a function there to convert it. I just forget the name of it. And there's a reverse conversion also. So if you have a standard formatted text string that is an IP address, IP6 or IPv4, it'll convert it to the internal. There's a conversion function that goes one way, and there's the inverse function exists also. So INET, like if you're new to Erlang, which I assume you are if you've stuck with me this far through the video, I assume a bunch of graybeards aren't watching this. This is an interesting module to look for. So if you go to a search engine and you type in Erlang INET, that's some interesting reading. And then read GenTCP also, because that's a pretty cool one. GenUDP is really cool too. And then GenSCTP will make you sad because no vendors ever decided to support that, but it's actually in Erlang. Anyway, we remember this, the client manager. After we get a client, we connect, we got the socket, we got a connection, we're passing the torch, starting up our successor. We're printing to standard out. Hey, I got a connection from this guy. So this is me, and I got a connection from this guy. We're going to print out to the screen. Then the next step is we're going to call the client manager and enroll to say, hey, I'm active now. I've got a user. So any messages you're getting, make sure you forward them over here. Then the state is just this. Now I've got that. Remember, this is a state record. I defined a whole state record. There's only one element, which is kind of like a waste of a record, except that if you are going to write anything interesting in here, any interesting service with this as a template, very quickly you're going to start adding stuff to that state record. So it's already there, which is like the point of a template, right? This is just a template that can run, but you'll start adding stuff to that state record like pretty quick. Then we go to loop. There's a main loop here, and what do you know? It's called loop. And of course, Erlang has no looping constructs. It's all recursive. So if we look, this becomes painful. This is the whole main loop right here. We come into loop, parent debug state. Remember, that's like the idiom, parent debug state. So every time we go back into our main loop, we're doing parent debug state are the three arguments. The first thing we see here is active once. This is a detail, and it confuses a lot of new Erlangers. The reason we use active once is because what this means is we're not doing C-style polling or pull weight or anything like that on the socket. So we're not checking for bytes that are in the buffer. we're going to defer that task to the Erlang runtime. And in our code, because that's a low-level detail that we don't care about, in our code, what we care about is receiving messages, right? And if I receive data from the socket as a message, and I'm also waiting for system messages, I can have a single receive clause that captures all this for me. Instead of having to figure out how to balance time between checking the socket for new data and waiting for system messages in a communication queue. The queue checking job can be merged into a single thing this way. So we're deferring that to the runtime, but we've defined our socket as active once. What that means is after the runtime detects data in the network buffer for us, it'll package that up in an Erlang message of this form, actually, TCP. It'll be labeled TCP. It's labeled with the socket ID. So we know, because we could be handling like 50 sockets, right? So to make this unique, it's not just any TCP message, it's a TCP message from that socket. So it identifies itself. And then the binary data, we've elected to receive these messages as binaries. We can also elect to receive them as lists, which I do quite a lot because lists are very convenient. People complain about it uses too much memory. Like, you can store like the Library of Congress in a modern computer's memory. It's not, lists versus binaries is not really that big of an issue. Especially for ephemeral messaging like this. You wouldn't want to store large data like that permanently, but manipulating text is easy as what we call I/O lists, and that's a different video itself. Anyway, active once, the socket is going to be active. We want to receive messages from it. So this is what inet set ops is telling the runtime. Send me data from the socket if it's there, but only do it once. So if network traffic comes to the socket, the network buffer, and the runtime sees that, it's going to clip that out, put it into a message, and send it to us as an Erlang message. And then the runtime is just going to let that buffer accumulate. It's not going to, if more data arrives on that buffer, it's not going to continue to send those to us as Erlang messages. It's going to wait. The reason for that is we have said we want to be active, but we only want to be active once. What that means is we're going to get a message. We can go through and do stuff with that message. Any arbitrary processing that we want to do initiated by the receipt of that message. Then we're going to come back to loop. You notice all these actions. So buy was our magic cue to close, right? So that exits. Any other message we're going to handle, echo it, and then loop again, right? So loop. We're always looping. Unless the socket closes, then we exit. Any system message, we're going to do handle system message, which actually winds up in a callback to loop again. And we can find that defined below. Let's see, that's system terminate. Continue. So system continue would be after the system, whatever the system task is done. It'd go back to loop again. So we're always coming back to loop. And the very first thing in loop is, okay, send me the next message. So this lets us receive messages one at a time. Let the network buffer push back against, if there's too much data coming in over TCP, that if that network buffer gets full, that'll push back against the sender. We are not internally accumulating a ton of network messages, or like we're not allowing ourselves to be buried under network traffic here inside of this process, because this is an Erlang process, so it has a mailbox. We don't want to stack it up with an arbitrary number of messages that maybe we're not fast enough to handle. So leaving it on the network buffer is natural pushback to the sender, because TCP, remember, TCP it's a protocol that has its own rate limiting itself, right? It can push back and say, hey, I can't acknowledge that message yet because I had to dump it. So you can get rate throttling naturally in this way. So that's why you don't always do it, but with most Erlang message-based socket handling code, when you're doing TCP in particular, we'll do active once to just get one thing off the buffer. And then once we're back up here again, which should be really fast, like, you know, I mean, this is Telnet, so you could have naughty bots out there trying to bury you under traffic, but humans are slow, right? So long, you know, eons before another message comes in from a user, we've already activated this and we're waiting. And if it wasn't activated, that data would have still been on the buffer anyway, right? So we're not missing anything. There's no way to miss traffic. Now, I say there's no way to miss traffic. This is where I plug my ears and I go, na, 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 and I pretend that TCP is flawless. It's not, but it's good enough that you can rely on it for this. So active once is an important thing, and you can't forget to put it in front of a receive if you need to receive a network message. That's the key thing. You'll write code sometimes where you're like, okay, I want to do some back and forth. I want to go to a special mode, and I'm going to do some back and forth with a remote node. And I want to receive a network message right here. And you write your receive clause. And then you test your system and like nothing happens. Your system can pass all the tests, but this is integration. You're talking about over the network here. Your module, you know, your unit tests can't tell you anything about, you know, the foreign land of the network. So it just stops right there and you go, why am I just halted? That doesn't make any sense. Why can't I receive data? And you'll like be pulling your hair out. And it's because you forgot to put this line right above your receive clause. You broke out of your main loop, so this didn't happen. You got a message. You go into some special mode to handle a message, like a special form of messages, and then you don't get anything from the client. Well, your system did. Your node actually got those messages, or it got the network traffic rather. It was never converted to messages because you never said active once right before that receive clause. So don't forget that when you're writing these things. So anyway, kind of running along here. If we want to create a new system replace state, this is like how hot code loading actually part of how it happens. We don't really need that implemented here for this, but you know, it's good to be complete. So this is a complete template. Anyway, if we want to, we notice here we're matching on the literal right here, by. If we receive the message by, then we're going to exit. If we receive any other message, we're going to print it to the screen, and we're going to tell the client manager to echo it to everybody. And then we're going to go back into our loop. Now, this is the point, this is the place where we could put a dispatching clause, call a dispatching function that evaluates the inside of the message. And depending on what the content of the message is, we might want to implement commands that do something different. So IRC has these slash commands, right? Slash join some channel or something like that. This is where we would put that in. We would do something like, so right now this is just here. Let's go to the bottom, and I'm just going to make a dispatch function. Dispatch message, and we're going to receive state. I don't care how this is done yet. We can leave this notification in kind of as a debug message for now, but what we want is and then we want that. So for now, we can just put this down here. Here. If we receive and we don't care. Oh, actually we do care about that, right? So that is simple. Oh, actually, we're just receiving OK up there, and this returns OK. And now we want to go back to this guy and get rid of that. Boy. Okay. So what we see, oh, and I'm silly. Look at this. I'm a silly person. We gotta, this message would match on anything. We have to put it at the top as it was above. So what we're seeing is that, remember, we saw case can be an opportunity for matching. Function heads are an opportunity for matching, which we've just done here. We've converted a receive is also an opportunity for matching, just like case is. So case is a match environment or a match possibility. Receive gives us a match possibility also, and function heads gives us a matching, an opportunity to use matching. And what we have right here is I've moved a match on by from this receive clause and put it in this dispatch clause. So let's see what happens. And let's see if I screw this up, because I may have. Also, remember I was saying that we could make the, we could put that listen to port number inside of this so that we don't have to do it manually all the time. We can do this down here. So we need this. Look, this returns something, right? It returns OKPID. So we're going to capture the result of that because it needs to go back. Then we're going to put what was it? Client man. We're going to go ahead and define this here, and then we're going to return result because we can. Now let's give this a try. Okay, variable state is unused in 157. It is indeed unused, and I don't care right now. So we should be up, and we should get the same effect that we just had, right? Blah. And we do, we get blah. So the cool thing about that is that what this means is we have been able to move this message thing from, instead of having a one giant receive clause, we can push this out to a dispatch that takes the state. We already have, here, let's do this again. Does buy still work? Buy still works, right? What that means is we've effectively moved the match up here to the match down here, which means that we can do other kind of neat stuff. Like, for example, we could do, what do we want to match on? Let's match on slash. And then rest. We don't need that yet. We'll just close that up this way. Now, rest would be, in this case, a command of some sort, right? This is how we would start implementing like we could do what? String split. That's not descriptive enough. Okay, so we're going to split this. What that's going to let us do is break the instruction, any instruction text off of the rest of it. Actually, we might want to chomp this too, right? Because we don't want that, the RN on the end of it. We can do string chomp message. What chomp does is it just removes this junk. Now what I'll do here is just indicate that Which actually, if I have if somebody enters something that like, what if there's no body to it, right? What if it's a command that's only a command? We can indicate that here if I stop typoing. Okay. So, whoop. Actually, we're just going to return OK anyway, right? So let's nuke that, and then same thing here. See if I typoed anything. What? Wrong number of arguments and format call. That's a cool error message. Oh yeah. I've never seen that before. That's neat. So that's like an Erlang release 23 thing that we didn't used to have. We used to have to wait until you try to call that before it says, hey, your format call isn't structured right. That was pretty slick. Okay, so we're listening. Let's connect. We'll connect the other guy just to make sure that we're not missing the message. Blah, 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 blah. Cool. Okay. Oh, okay. Remember, we chomped these, right? We chomped these messages. And a side effect of chomping those messages was that we removed the RN from the bottom, or from the end of them, which means that we actually need to add those back when we issue our echo command. Where was echo in here? Ooh, that's... I'm silly. We don't need that way. Okay. I think that's the right, should be the right thing. So let's move back over here. Okay. Yep, that worked. Blah. Okay. Now we're getting our returns because we were actually sending across the wire something with no line terminator, because we chomped it off so that we could evaluate the messages in more of a clean way. And then that bit was missing, so we were echoing something that was like had no tail. So anyway, foo. Okay, so see, we got that. What if I wanted to make a join channel command? Join Erlang. Receive join Erlang. Which becomes receive instruction join with body Erlang. Aha. So you can see how we would start. This is the beginning of implementing chat operations. This is how we would get started with it. We can parse the incoming data. We can match on special cases and still accept anything that doesn't match as a naked message and just echo it to everybody. Or we can start creating commands like join. So this is how you would start. This is the very beginning of starting a chat system. And it doesn't take much time. The explanation took time. But actually doing it is like really quick if you've done it before. Or even if you haven't done it before. You've gone through this with me now. So getting your own thing started and to start doing your own experiments is like cake at this point. I don't have time right now. My day has to move on. But if I do find a little bit more time, I think it would be fun to demonstrate how to implement chat channels as a separate service. Remember, this is all happening inside the client service. It's the only service we got right now is clients. There's no channels, no concept of that. But how would we go from this single thing that is a, it's a client, it's a client handler that just echoes messages to everybody, and we've got the beginning, the stub logic necessary to implement some commands, but we're not doing anything with them yet. But we can see how the program structure would start working right here. How would we implement chat channels so that only when you send a message to a channel, only the people in that channel get that message? How do we divide that up? How do we make those channels exist? How do we manage those channels? And so on. What are some good kind of idioms for doing that? Because the reason I think that's an interesting thing to address later is you'll find that managing chat channels provides a template pattern for a lot of things that you do in totally different types of services. Whether it's in a game server, you have instances, and each different instance is managed by a monitoring process. There's not much difference on the back end side. There's not very much difference between handling like a dungeon instance and a chat channel. Only a certain number of people are members of that instance. They should only have visibility over the traffic within that area, within that instance. It's very similar to managing a chat channel. And we'll find, this recurs all over the place. So how do you make a subservice next to this, and why is it next to it? Just because the world crashes, just because the chat channels crash, you don't want to kick everyone off the system. They should be able to discover, the chat channels are gone. Let's remake them and just repopulate them. If all the clients crash, now in our case, we're not saving any data, right? We're not logging anything. We don't have user names we're not registering anything. But if we were going to keep a chat log, like let's say we wanted to change this into an image board, the way that an image board code works, where you have the last 100 messages are current, and then anything older than that gets thrown away. We would want to save those last 100 messages so people could see the most recent discussion buffer. And I say image board. This isn't web, but it could be. There's no reason that we could plug a web server right into this, and we'd have two interfaces, Telnet and web, right? We wouldn't want to lose existing channels if they had persistent state that we needed to keep track of. Even if the state wasn't persistent, in the sense that maybe it's not on disk, maybe we just keep it in memory, and if you reboot the system, that all gets wiped out and you don't care. But for convenience, if you haven't crashed or restarted, you can see the last recent message discussion buffers. If that was a feature you wanted to provide, then all the clients crashing should not wipe out the channel data, the channel state. So we'd want these separate services. We wouldn't want them under one big God supervisor with a single state process that knows everything, because if anything goes down, everything goes down. That's bad. So how do we separate those into their own little zones there as subservices? So that a channel service would look very similar to the client service, right? We would have the channels would be the name of the top supervisor, because that's the service we're discussing. So channels. Then we'd have channel manager. We'd have channel supervisor. And then we would have channel processes that are workers. The same way that we have clients, client manager, client supervisor, and the client processes that are handling actual connections. That same structure. It's four module definitions. And more than half of it is, half of them are just straight up boilerplate, right? The supervisors, that code almost doesn't change at all. The manager code is pretty similar, and the cases I'm discussing here are fairly similar, but you may want to put some conditions into the channel manager code. Like, for example, different channels themselves may have their own rules, administrator rules, but you may have system-wide rules about availability of channels, or if someone's even allowed to communicate with the channel or not. those, like, if you ban somebody from joining all channels except for administrative channel, to where people would like plead their case to get back in the system. That's stuff that you can't define in each different channel, right? You'd want the channel manager to know rules like that, and that would be state that you don't want to lose. Just because the clients, you could have a malicious user that says, oh, if I just crash the system, then it'll reset everything and I'll have, carte blanche again. Well, he'd be wrong, because you could crash the entire client service. The channel service would be unaffected. And when that comes back up, the channel data is still there, safe and sound. So that's an interesting thing to do. I don't have time to do it right now. I'm running too long on time at the moment. It's already 4 o'clock. So anyway, I think it would be, if anybody found this helpful or useful at all, let me know, and I will move forward. I'll just take this code, put it in a repository, and we can move forward with it to actually making chat channels, because I think that's an interesting and useful exercise for people to see, because it shows so much about how you do services that are sitting next to each other. So anyway, this was fun. You can feel free to take anything in here and use it. I didn't do much beyond the template itself. I spent most of the time explaining things. I think I've exhaustively explained this template at this point. So use the X template in Erlang project and just mess around with it, because it gives you a Telnet chat, a Telnet echo server by default, and you can change that into anything you want to do. So anyway, have fun coding, guys. As always, I hope I didn't bore anyone too much, but as I always say, this is streaming media. You can just turn it off. So anyway, if you got this far in the video, thanks for sticking with me. I'll look into doing the chat channels thing later on. That could be a lot of fun. So bye-bye.